All right, let's do it. Okay, I will totally selfishly admit this is like my favorite lecture of the quarter, but it's super theory heavy, and I like to think that it's theory fun, but I do save it for the very last lecture of the quarter because I assume it's something that only a subsection of folks want to know about. But what did I just find in my pocket? Before we get into it, there is a warm-up today, but it's just a for funsies one, so feel free to put something in there to mark your final lecture attendance. Then otherwise, let's make sure that we get through any of these final announcements. So if you have any questions, I want to make sure that we address them. So I know I promised that I would update the Canvas with all of your resub calculations. That should all be in there. So now your resub score in Canvas should be the larger of your two scores between your original submission and your resubmission. Meaning, if you for some reason got a lower score on a particular question on your resub, I went back in and replaced it with your original score, because the resub, you should not have a lower grade than the original submission. So the resubs and the midterm should all be in there. I will apply the same logic, of course, to your final exam resubmission. Reminder, today is the last day of office hours, so there's no TA office hours next week. However, we will be paying attention to ed, so if you have, further questions, feel free to post them there. I also did add a large amount of availability on my appointment calendar. So for example, if there is a grade that doesn't look the way that you think it should look, or you have any general questions about this course or careers or whatever, I am happy to meet with you next week. There is my bit.ly again, of course. And then essentially what we're going to be doing between now and Friday of next week is just finishing up our grading and making sure that everything in Canvas looks the way it's supposed to look in Canvas. I know if you have sent me an email in the last 2 or 3 days, my email is thick right now. And I promise I see it in my email and I shall get back to you. But if you are concerned that I have forgotten something I promised you, feel free to ping me. Feel free to send me another email. I am happy to do it. I just am sort of working through things one bit at a time. But if you have any concerns, like something on the Canvas does not look the way that you think it should, please send an email to the instructor's alias, because obviously GradeScope is how we actually collect our grades and distribute them to you. But I have to use Canvas to make your final GPA, insert a bunch of FERPA, blah, blah, blah. So make sure that Canvas looks the way that you want it to look or you expect it to look. And if you see any issues there, please send me an email. Probably, like I said, by end of day, Thursday, early of Friday next week, all of our grading will be done and everything should be in Canvas. And then, of course, a reminder, because I know you had an amazing TA that definitely made this insanely difficult class a little bit easier. You should nominate them for Bob Bandis because it means a lot to them. It meant a lot to me when I was a TA, so you should do that. That would be cool. Okay, I think those are all of my announcements. Does anyone have any administrative questions I could possibly answer for you at this time? I guess them all. Should we look at the poll everywhere? What are the vibes? Let's take a peek. Okay, let's see. Oh, I forgot to activate it. Nobody mentioned. Okay, I'm going to activate it. Go ahead, fill out the poll everywhere. How about we'll look at it at the end then? The poll everywhere is now actually active. If there's no other questions then, we're going to move into our topic for today. Okay, so we're at the very end of this quarter, and I know sometimes 373 can kind of feel like a somewhat random collection of topics, but if you remember way back in lecture number 1 of my analogy for how we're learning to code, what you are learning is a new form of communication. You're learning a new art, if you will. And before you can really get into those things, you have to learn, the foundational pieces. So I think of the intro course, maybe like 121 is vocab, and 122 is grammar. 123 is maybe like putting together your first paragraphs. And this class is all about creative writing, right? This is the artistry. This is where you're starting to hone those tools. I'm going to give you some abstract problem. Your very complicated and incredibly advanced human brain is going to look at that abstract problem and figure out how to reach into your toolbox of computer science to solve that problem. That's most of what we've been doing up until essentially the last couple weeks, when I have to fill up the course with other things that I can't necessarily put on a programming assignment. And so if all of the different data structures and algorithms were the different art techniques you've been learning, the last week, maybe 2 weeks, is like art history. And I feel like you need the context sometimes to really understand how all of those tools came about and why they're so important. But just to be annoying, this is probably like my most art history-ish of the lectures. So we are going to talk about the largest unsolved problem in computer science. Some of you may have heard of it. It's called P versus NP. But before we get into it, let's do some history stuff. So the field of computer science is not actually about how we type Java code into this type of electronic device. And in fact, if you get really deep into academia, there are a bunch of computer scientists that think programming is not even considered computer science, because that's not the science of it. Computer science is about how we find ways to use computers, in the abstract definition, to solve human problems. It's about the translation of the complexity of human issues to the simplicity of the digital computer. Fun facts. This is a picture of what is considered the first real computer. It was designed in 1837 by a gentleman named Charles Babbage. It was invented to compute Bernoulli's numbers. It is obviously not electric because it predates electricity. If you can kind of see, there's like a little space here. That's where you would feed in the cards that would program it. And it is based off of the automatic weaving looms that the Luddites were originally protesting way back when. The first ever computer program was a program designed based on just the schematics for this by a person named Ada, Countess of Lovelace. She just read the schematics for this. It had never been built, invented a way to perform Bernoulli's numbers, wrote it all down, could not even try it out because the machine didn't exist. And then she died because, I don't know, typhoid fever or something that was happening back then. Over 100 years later, in 2010, somebody went and built this. This was built very recently. And then they were like, let's see if Ada's program works. And they just did it, and it did work, except for one off by one bug, which is wild. But this is just really to demonstrate to you that all that was happening there predates transistors, predates electricity. It's all just about how to look at the complexity of the human world and translate it into some type of programmable device. Then by 1943, we've started to use actual electricity. This is the Harvard Mark II. If you go to Harvard campus, they still have a piece of it, and I have a really cheesy picture of me in front of it. And this was when we really were starting to use electronic devices to solve massively complex problems that humans could not even solve themselves. Unsurprisingly, it was first used for war because America? I don't know. But more fun fact, this is the origins of the term bug. Does anybody happen to know what the first bug was? You're probably right. It's funny. Anyone? Yeah. It was an actual bug. It's a moth that flew into this machine and short-circuited one of the vacuum tubes, because this also predates transistors. And they had to, at this time, physically crawl into the machine to debug it. And there's a picture of said moth also. You can go look at it. Fun stuff. Then we moved into the 1960s, and we started to use transistors, so computers started to get a lot smaller. In 1968, that's when we started to get the idea of like the mouse and video conferencing, the idea of Windows, meaning that your computer could run multiple programs at once. Actually, every single one of those things was invented by a gentleman named Douglas Engelbart, who was a researcher at Xerox PARC, and he did all of those things in one day. And then someone named Steve Jobs was there and stole those ideas. That's a real thing. Steve Jobs technically stole the ideas for Windows. Also, because if you can't tell, I'm not a big fan of Steve Jobs. He also stole the idea for the Apple computer, which was actually invented by an incredible human named Steve Wozniak, who is still alive, and left his big fancy tech career because he was working with someone who was unkind, Steve Jobs. And now he teaches high school computer science in Palo Alto. But this is the Apple II, the first commercially successful computer program. And the real magic here is you can see it is now generalized for the population. So by the time we get here, it's not so much about computing specific numbers or missile trajectories. It's starting to think about how can computers become a generalized tool to solve whatever problem humans can come up with. That leads us to 1970s, where we're really starting to explode the world of computer science research. At that time, there was a bunch of mathematical problems that had existed for periods of time. And because things like the Apple II and other types of devices were starting to proliferate, those researchers were like, I wonder if a computer can solve this problem for me. Now, some of the problems that we as humans had been trying to solve for a long time could be solved with the computer. Because the thing the computer's really good at is trying a bunch of different things really quickly, right? Like if I'm just trying to find some path through the graph, well, a computer is much faster at just checking if every path is possible than, say, we as humans would. But as they were doing it, they started to hit some issues where not every problem seemed to be solvable by computers, but some problems were. And so when they realized that, because they are smart and smart people bring their brains together, they were like, what's different about the problems that can be solved and the problems that could be solved? In fact, can we rephrase the unsolvable problems in a way that they are now very similar to the solvable problems? This is actually something called a reduction. It's essentially just the idea that you look at the abstract or the meta level of your problem and relate it to another problem so that they are essentially equivalents of one another. I.e., if you solve your problem and my problem reduces to your problem, your solution works for me. So they went through and actually put together all of those problems in a physical book, which is fun. We're going to talk about it. And they started to classify these problems. Which ones were solvable? Which ones weren't solvable? What makes them related to one another? And this is how we entered the world of complexity classes. That's why all this time, you might have seen my little symbol, it's technically in the set of big O of n, and that we drop all the coefficients and all of the lower order terms, and we kind of make this big bucket of anything that runs in linear time. It's called a complexity class because it's supposed to be a general grouping of how these problems runtime relate to each other. Because what's actually interesting about complexity class research is not just finding the big O, which is important. I swear there was a reason we did that for 10 weeks. But actually starting to figure out how these problems relate to one another. In that collection of things that were solvable and not, once they started to assess how long things took in relation to inputs, they created what they would call the P complexity class. The P stands for polynomial, and it is a set of all decision problems that essentially can be run in what we call, quote, quote, efficient time. Really, what it just means is anything that runs in n to the k time or faster. So constant time, logarithmic time, and linear logarithmic time, n squared, n cubed, all of those are in what we would call polynomial time. And what's magical about them is that these are now all fast enough that pretty much for any value of n, we can still have a computer accomplish that task in a reasonable amount of time. What do I mean by reasonable amount of time? It actually turns out that when problems have a very inefficient runtime, not only will they not run on your device, but they actually won't run on any device. In fact, for example, recursive backtracking, which runs in, say, k to the n time, where k represents the number of choices, not unlike Fibonacci, where it's got 2 recursive calls per singular recursive trigger, so it runs in 2 to the n time. Those are not polynomial runtimes. Those are not considered efficient. And so very quickly, as n gets bigger and bigger, you run out of computers that exist that are able to run that program in an amount of time where we humans would still be alive to see it. So for example, n cubed, where n is 100, this is considered efficient, that could take up to 3 hours on a supercomputer to run, that kind of thing. Here is a great example. So you can see when n is these values, we can pretty much always run anything in log n time, we can run anything in n time, so on and so forth. But once we start to get to 2 to the n, these little stars here, you can see the amount of time it takes 10 squared. 10 squared is 100? 1,000? Thank you. I'm bad at math. So 2 to the 100 would take 4 times 10 to the 11 years to finish computing. And it would take so long for, I assume then this is 1,000, and even more, that it would take more than 10 raised to the 1,000 years for the computer to execute. So that's why, look, you can kind of see there's this magical line right here between polynomial time, which is all of these complexity classes, and anything to the right, which is what we would refer to as exponential time. And so that was one of the things that the researchers realized right away, that seems to be a very clear demarcation between the solvable problems and the unsolvable problems if something can run in polynomial time versus exponential time. This is just FYI, we're going to start to talk in theory language. And so when I'm talking about relating problems to one another, hopefully at this point you understand a lot of the science or art of computer science is how we translate things in a way a computer can understand. So we are now going to talk about what are referred to as decision problems, i.e. some problem that can finish with a yes or no answer. Because you know, computers don't like gray area, right? It's got to come out to either a true or false answer. That's what we're working towards. So if we have a set of problems that can run in polynomial time, great. We have computers working on those. But there was this other set of problems that they did not have a solution for yet, but it felt weird that there was no solution for it. These were problems like puzzles. These were problems like traveling salesmen, where it feels like you should be able to solve it because if I give you the solution to the problem, it's very quick to identify that it is a solution. This is another complexity class that they came up with to try and define this set of problems that were unsolvable. It's called NP, and it stands for non-deterministic polynomial time. And it is the set of all decision problems such that if there is an answer yes, the proof of that could be verified in polynomial time. That's a little hard to understand, but let's break it down. The idea is that if I ask you some of these unknowable questions, and then some other way, some other just try all the options kind of way, you show up with an answer. It takes a very polynomial amount of time to verify that answer works. For example, maze solver. If I gave you a maze and I gave you the solution to the maze, it's actually pretty efficient to just like walk through the maze according to that solution and be like, yep, it works. That runs in a very efficient amount of time. Also, you know, we have these other ones. I'm not even going to go through them too much. But like if I asked you for the shortest path and then you gave me the shortest path, I would like walk through the shortest path and be like, oh yeah, it does connect those two vertices. Verified. So something has to happen to find the solution. But if the solution exists, I can verify it in polynomial time. So this is the unknown question. If some type of problem has the type of solution that could be verified in polynomial time, does that mean you can also discover that solution in polynomial time? So if it's the type of puzzle where I give you the solution and you can quickly tell that that solution works, does it mean that you can also quickly find that solution? And when you think about it from a computer scientist perspective, it's like, wow, I mean, it's got a limited set of variables. It's got an algorithmic way to verify the quote certificate or the solution. So shouldn't there be some algorithmic way to get to that solution? As of right now, not only do we not know if these things are equivalent, we actually can't even prove that they're not equivalent. So even now, if in your brain you're like, oh, obviously, Casey, just like verifying the solution doesn't mean you can find the solution, no one has proved that either. This is the conundrum that we are talking about, the P versus NP mystery. It was first posed in 1971. It has sort of lived on in the imagination of computer scientists still then, and only grows in interest, and we still have no formal proven answer. Here's a way to visualize what we're talking about. So let's imagine the set of problems we are trying to solve with computers. Here in the gold area are the problems that we can solve in polynomial time. These are things like sorting. We can run sorts in n log n. That's great. Maze solvers, finding primes, MSTs, all of that stuff. We did that in these classes. But NP problems, these are problems where if I gave you the solution, you could verify it, but I don't know how to find the solution as of yet. And in this category is a bunch of very interesting things. For example, the knapsack problem, which was on the dynamic programming slides that we showed, because if all you did with the knapsack problem was just try absolutely every single thing in and out of the knapsack, and it grew in that recursion tree, that's exponential time. So you can only solve knapsack without dynamic programming up to a certain value of n. Other things that are interesting is the traveling salesman problem. The traveling salesman problem is one in which if I give you a set of stops, return back to me the shortest path where you hit every single stop and then return home. I also kind of think of it as like the Amazon delivery problem. You know, like if a truck leaves the warehouse, it's got to do so many drop-offs. What's the shortest possible way to leave the warehouse, do all of your drops, and return? Right now, that actually is not a P polynomial time problem. It's an NP problem. So if I gave you the route, you could be like, yeah, that's a short route. But we do not have any efficient way to actually solve that problem as of right now. And then we have like the exponential problems. These ones down here, these are ones where the computer scientists have proved there shall never exist an efficient solution to this. They are a category unto their own. A lot of them are like, what's the best chess move possible? There's just so many permutations that unless we say achieve quantum computing, we do not have computers that are smart enough to always pick the absolute most perfect optimal chess move. Now, we do have computers that have used AI and ingested chess notation for possibly over 1,000 years, and they've learned how humans do it, and now they mimic how humans do it. But the computers cannot figure out how to do it themselves. They can only figure out how to mimic human behavior based on human statistics, which is another interesting thing about the core nature of how our brains work versus the computer. So, what can we do to try and find a solution to P versus NP? So, well, we've got all of those problems in the NP category. It feels like if we could maybe solve like the hardest problem in the NP category and prove that it runs to find a solution in polynomial time, well then maybe that like by extrapolation means the easier ones will also be in polynomial time. So if I'm trying to prove this entire complexity class could be solved efficiently, I'm going to pick the hardest one and see if I could solve that one efficiently and hope that then the lessons I learned from that will apply to the others. So that's what they started doing. They literally started looking at all of the different research projects happening in the 70s, and they were like, what is the hardest unsolved problem that you have? We're going to see if we can solve it. So what they did in order to try and figure those things out is they started to look at the relationship between these problems. Are these problems other problems secretly in disguise? Are they problems that are essentially trying to accomplish the same thing, but there's just a slight different context around them? There's a slight different phrasing of how we pose them to the computer. An NP-complete problem is the hardest problem in NP if it is an NP problem and all the other problems in NP reduce to it. So if I can solve this problem, then I could solve every other problem by extension, because then it's just a matter of reforming things in this way. So they add a third category they call NP-complete, which essentially then becomes a way to universally encode these difficult problems. Can we come up with a language, a symbolic language, to represent all of the NP problems? Because then we have shown what is shared across all of them from a logic perspective, and now instead of having to solve them all individually, we just have to solve this one. So they realized, okay, well that would be great, but like, is there such a thing as a problem where all other NP problems reduce to it? Is there truly a universal language for these hard problems? That can't possibly exist, right? Spoiler, it does exist. In 1971, the same year that they posed the PNP problem, two separate individuals that happened to live on either side of the Iron Curtain, which is why they both get name credit here, independently came up with this theorem. This sentence and its accompanying, I think, like page-and-a-half proof, won both of them a shared Turing Award. The Turing Award is our Nobel Prize, for context. Big deal. This was the problem. This idea of Boolean satisfiability. How do we look at problems and abstract them away from their context to just the logic of satisfying variables? So, you have different levels of satisfaction based on the number of variables you're trying to satisfy. 2SAT is a set of Boolean variables and a list of requirements where each individual entry has two possibilities, either of which must be satisfied. So variable 1 must equal true or variable 2 must equal false. One of those things must eventually evaluate to true. So you could kind of see this as being like in between an if statement, and we would have to figure out some type of pass through that if statement. It's just a way of isolating what problems are trying to solve into their variables and the states they must be in, and then feeding those set of requirements into the computer in a way that it can understand, because the computers are really good at understanding Booleans. 3SAT is the exact same thing, except instead of having 2 variables per entry, you have 3. 2SAT, as it turns out, and once upon a time I used to do an entire lecture on 2SAT and actually show you the proof of it, and then I realized it terrified all of you. So I'm just going to show you the final slide now. 2SAT, you could recursively backtrack it and just try every permutation of every possibility and then check if it satisfies your list of requirements. But there's actually a really clever graph reduction using topological sort and strongly connected components that reduces the solution of 2SAT to linear time. So anything that you can translate into this type of 2SAT language can be solved in linear time. And in fact, there are things called SAT solvers out there, where if you can reformat your problem in this way, you just plug it in and then it spits out your answer. And scientists were like, that's incredible. We did that for 2SAT. There must be a way to do that for 3SAT, right? We've been trying to do it since 1971, and so far, no luck. But to help us as we move along in our frustrations, they started to do the reductions to see what can be translated into 2SAT versus 3SAT. And so every time something could be translated into 2SAT, they were like, great, here's your solution. And researchers everywhere rejoiced because they all essentially just had to copy off of each other. Shout out to researchers in the 70s. But there were some researchers that were like, no, I can't reduce mine to 2SAT. I can only reduce it to 3SAT. And then what that meant is, instead of having one NP complete problem, one problem that if ever solved would solve all of these problems, suddenly we had over 100. We don't have a solution to them yet, but we know there's something special that connects all of them. And that if we find the key that unlocks one, it will now unlock all of these. Can you understand why this obsession with this problem grows? Because now, as you can imagine, so this was Karp's theorem in 1972. So within a year, they found over 100 problems that all were related to another using the 3SAT language. By 1979, they actually were publishing a book. It had over 300 of the world's biggest unsolved problems and all of their reductions so that they could be solved if we ever solved 3SAT. This is a book. I actually do know some of the profs here that have like the original one sitting on their shelves, which I think is interesting. This book, actually, in 2006, they did a big research study of what is the most cited piece of academic research in all of computer science. It's this book, still and forever. Because everybody just keeps trying to ask themselves, is the problem I'm trying to solve actually solvable? It's a good thing to start with before you get too deep in, right? And every time you find that the problem you are trying to solve actually is 3SAT in disguise, meaning it's NP complete in disguise, we add it to the list. 1979 is the last time they actually bothered to print them out and put them on paper, because now there are thousands of these problems. In fact, I went and did a query. You can click on this query and read all of the different ones they just published in the last month, for example. Here is a Wikipedia article of some of the most impactful ones. Some really famous problems appear on this list. So now, the treasure behind this singular lock grows almost daily. You can imagine, again, the obsession. Now, it is a little bit, again, about phrasing. So, shortest path, we ran using Dijkstra's, right? It runs in graph linear time. It runs in polynomial time. You would feel like if I just invert like an alligator mouth somewhere, or instead of using a min heap, I used to use a max heap, then longest path should just run in the same amount of time. But it turns out, nope. For some reason, and I'm sure there actually is reasons I'm not going to go into, longest path actually falls into the NP complete category and does not finish in polynomial time. Question?
Yeah, I was going to ask if AI is like able to do reduction, or if it can like translate a problem that you give it.
Is AI smart enough right now to do the reductions for you to determine if your problem is actually an NP complete or an NP hard problem in disguise? It does depend a little bit on how you interact with it, but yes, because if you think of what AI is, all AI is statistics. And so the reality is every time you have a problem, if you're trying to figure that out and you plug it into AI, if somebody else has ever posed anything similarly, yeah, it could. Yeah. Was that?
Not like it can like logically do it.
Yes, because AI is not creative. AI is doing nothing but artificially simulating the way all of your brains work. So if no human has ever done it, AI cannot do it. Yeah? What a great question. So what happens if you solve PNP? Okay, hang on. Oh yeah, traveling salesman, okay. I don't know why it's, hang on. We're gonna let it think for a second. Yeah, honestly, we don't need to talk about those. So, let's talk about the implications. What happens with this whole PNP problem? For the record, most computer scientists, like if you ask them like gut check wise, they don't think P and NP are in the same category. I'm going to explain to you why I don't think that on the last slide. But if you prove that P and NP are not the same, if you prove that just having a solution does not mean you can efficiently find an answer to it, well, first off, you will automatically win $1 million, which feels very small these days, but used to mean a lot, from the Clay Mathematics Institute, because the P versus NP problem is one of what they call the millennium problems. There were 7. One person solved one of them. There's 6 remaining. Of the 6, the PNP is the most famous. And if you prove that P does not equal NP, you will instantly win $1 million. You will also quite obviously win the Turing Award for that year. But let's be real. Alan Turing, who? You will be the new name for the Turing Award. Sorry, Alan Turing, you are an icon, and we all owe you so much. Okay, so what happens if, to our friend's question, it goes the other way? What happens if P does equal NP, and thus there exists a key to that lock that will break every single one of those problems? Well, obviously, go get your $1 million, because cool. Let's see. But then also go and solve all the other problems, because every single one of the millennium problems is an NP complete problem, and then you could use your magical key to solve all those problems. But shh, don't tell anybody. Just be I'm really good. And then, you know what? You might as well just put all mathematicians out of work. Because technically, all math problems could be encoded into computers, and if you could solve all problems in efficient time, then you could solve every math problem that's ever existed, because symbolic reasoning. Why stop there? Technically, all of the things that keep us safe in computers rely on the fact that it would take too much time to just try every permutation. This is how passwords work. That's why, when you start to try a bunch of passwords, they lock you out. Because that's the only thing that really is keeping you from breaking into absolutely every single bank account on the face of the planet, is that you do not have a computer that is powerful enough to try all of the permutations for every single character for every single password. So if you had a solution to PNP, then just I don't know, go wild. Whatever you would do with access to every bank account that has ever existed, or every financial transaction that's ever existed. This also would unlock every single piece of information that's ever been stored digitally. Read anything you want to read. No more secure online shopping, no more secure online banking, no more secure online messaging. All of that stuff, all encryption is, again, based on the idea that they just come up with a really complicated algorithm to obfuscate the real answers, but now you can instantaneously crack any code. So do with that what you will. But also, so much of the world now relies on computers. We have figured out how to translate even our human anatomy into a series of letters. Protein folding and DNA can all be transcribed into the computer. And instead of just having a bunch of, I assume, pipetting, I don't know, anyone in a biology lab, you could just run the computer and try every possible combination of every possible protein until you finally find a cure for cancer. Yes, there are people that are trying to cure cancer this way right now, just running a lot of permutations and hoping that, they get a best case scenario and find the thing they're looking for at the beginning of the linked list instead of at the end. The world where P is equal to NP would be very different, because we rely on the fact that just because you know the answer doesn't mean you can find the answer. But what does that mean more at its core about how our human brains work versus computer brains? So like I said, pretty much most folks agree that P is not an NP and that there doesn't exist this mystical key that shall unlock this treasure trove of all of these things. Because even though you know it when you see it, you can't necessarily discover it. And the key there is because when you are trying to solve problems, there seems to be something that happens in the human brain, in our physical anatomy, that we call creative leaps. And we don't fully understand them. It could be half memory of something you've heard before combined with a dream. We don't know where these leaps in logic come from. But the reason that AI can't do anything that you haven't already done, the reason generative AI just steals from other artists, is because computers are not creative. All they can do is mimic us. And we keep trying to teach computers to be creative, but they are missing the creative leap. And each of these hard problems, like the 2-sat situation where I was like, okay, we were trying all the permutations, but then boom, we realized that there was actually a more efficient linear way. A computer didn't find that. A human realized that they could reduce it to a graph and do strongly connected components and apply topological sort. A human had to find that solution through the connections, through some magical inspiration that happened inside of their head, and we have not been able to replicate it in computers. This is my favorite sort of quote about it. So if P equals NP, we would live in a very profoundly different place than we would. And there would be no value to the special creative leaps. Computers everywhere could perfectly replicate everything that our brain is able to produce. And suddenly that line between artificial intelligence and our human cognition would essentially evaporate. Because then there would be no fundamental gap between solving a problem and recognizing the solution once it's found. Everyone who could appreciate a symphony could be Mozart. Everyone who could follow a step-by-step argument would be Gauss. But that's not the way the world works. We have some magical genius inside all of us until maybe somebody actually solves that whole quantum computing thing. Like, ask me again, maybe later. But this is why I personally do believe that P does not equal NP, and we are not likely to find this solution anytime soon. Question? So who knows? Quantum computing does not technically exist yet. Obviously, we have an incredible research arm here, but quantum computing, if you think about what's really happening, is the way that our brains process information is still very unknown to us because we are taking in constant amount of information at such a volume, we can't really fully explain it to a computer. Like, we can't really fit in all of our visual data and all of our sound data and all of our touch data and all of our memory into a way that a computer can even really fully comprehend yet, even though people are trying to do the imaging. I know. Insert comment about people trying to live their singularity dream and download themselves to a computer. We can get close, but we do not have computers that can mimic the incredible complexity of what our brain can do. Quantum computing is the attempt to try and totally redesign how computers think and store information in a way that would much more closely resemble the magic that happens inside of our skulls. And I don't know enough about it to tell you whether or not that's going to happen in 10 years. Maybe somebody here will tell me in the future how that shakes out. Maybe we will have some type of, bicentennial man singularity life in the future. But at least for now, the reason that AI will never replace you is because AI will never be creative. And you have some magic in you that solves problems in a way that we still don't understand. Yeah? Oh, yes. So whenever you say create a new random object and call ran.nextInt, that's not true random. True random does not exist in computers because it's actually formulaic, but usually what they do is they use the clock to seed it. So there's a number that's constantly changing. They do a bunch of really complicated algorithm, changes to get a number. It's also technically, you can go out on the internet and learn about a bunch of very clever hackers that figured out how to reverse engineer the randomness algorithms in slot machines because those aren't technically random. So there is usually a really complicated algorithm that's obfuscating it, but you can almost always reverse engineer that algorithm if you give it enough time and you have enough information. They did get arrested, for reference. Those folks, they made an app that they held in their pocket, and then as they played the machine, they tapped in the app what was happening, and they had built a reverse engineer of the random algorithm into the app, and then it would vibrate to tell them when to bet big. And they cleaned up for a while. Shout out to them. Yeah. So randomness, kind of not unlike what's happening here, requires this sort of creative jump. It has to come from somewhere in your brain that is not predictable. That's what random means. And right now, computers are entirely predictable. There is nothing about a computer, even though I know it feels differently sometimes. There is nothing that a computer can do that we can't in some way reverse engineer or find where it came from or whatever. But there are plenty of thoughts, dreams, feelings that no scientist or human can ever understand truly where the origin of it came from. Other questions? Thoughts, feelings? Yeah. It's not totally unrelated, but also I did not grow up with enough money to purchase an Apple product. Don't worry, I have similar hatred for pretty much all billionaires. Sorry. But Steve Jobs just was so mean to Steve Wozniak, and what an incredible icon. Wherever you are, Steve Wozniak, we're so lucky to have had you. And he was in a very toxic relationship, so I get it. But I guess Steve Jobs had good aesthetics. That's what his contribution was. Something about, yeah, those machines are pretty. It's true. I'm not going to lie. Get it. Yeah, question. I think if we prove P equals NP, it means that we will have figured out what the creative leaps are. And I think if we figure out what the creative leaps are, then we could probably teach a computer how to do it. And so then, yeah, I don't know, iRobot or something, weird stuff would happen. Yeah. So P being equal to NP means that, I love this example, every single person would have the genius to write a Mozart symphony, because absolutely everything that we experience, we could recreate ourselves. That's what PNP would mean. Yeah.
So if it were to be solved, it seems like a lot of different kinds of fields would be needed, like biologists and stuff, people who study humans, not just the.
I think so. I think to really understand this, we have to understand the nature of how human thought works, and that has obviously a lot of implications to philosophy all the way down to biology. Yeah. Correct. So you get $1 million and the Turing Award named after you, even if all you do is prove that what a lot of us already believe is that they are not equal. But we still can't even prove that. Okay. It's one of those things where it's technically not disproven in formal logical proofs. It's disproven in that everything we've tried hasn't worked. But I think, isn't that technically how we know gravity works too? Somebody, I'm so sorry, correct me. We just haven't disproven gravity. It's just it works every time. So we're pretty sure gravity is real. Any other questions, thoughts? Yeah. Yeah, they're looking for a mathematical proof using symbolic reasoning and that sort of the formal structures of that type of proof logic.